Okay, so went to the solution. We came with this over here. It took some work, but it was basically a pretty easy integration problem. Figuring out the constant was also pretty easy. So what I want to do is go talk about using software now, and I'm going to graph the direction field. I'm going to use Euler's method to graph a solution to that, and I'm going to graph out the solution we found by integration. So let me go to Grapher. We should be getting a little better at this. So the first thing I'll do is the direction field. And what's that going to be? The derivative of x with respect to x is 1, the derivative of y with respect to x is x divided by y. So that's the first thing I put down, this over here. It's a direction field. Now granted, it's kind of busy looking at it, and what curve goes through that. You could do a variety of curves over there, but again, you may not know what the curve is. All right. Now looking at it, I may just get a gut feeling. It looks like a hyperbola to me. I mean, if I follow those things, it looks like hyperbola. And what I'm going to do is try to draw a solution through that. And the solution I want to draw through that is it's a branch. It looks like a branch of a hyperbola at this point. So it's y prime is equal x over y with the initial condition y0 equals -3. And I got that curve over there, and I'm using Euler's method to do that. All right. Let me just go through the inspector now, and I'm going to see what the step size is. Well, the step size is 0.5. That's a pretty big step size, by the way. But I also want to graph out the solution we got, and we got the opposite of the square root of x squared plus 9. And if you look at it, I mean, for the bottom line, let me just zoom into a region of it, like this region over here. You'd see there's separation over here. And what I want to do is I want to start changing the step size. And I got 0.5 over here. Let's try 0.4. It should become a better fit, but I got to refresh the screen now to get that to change. Now, granted, it's not a substantial change. Let me just keep going. 0.3. Machine's doing the computations, but I'm not doing it. Hit the refresh. Got a little better, and you could keep going with this. And I'll do let's do 0.1 now. Let's refresh it. Yeah, it looks like it's almost the same thing. There's a little separation there. And let's go to, a 0.01. Right, it's even finer. And at this point, I'm going to hit the refresh button again. And you see no change. Now, someone says, if you zoom out, will you ever see a change over here? I'm going to say not the highest resolution over here, but you start to realize it's a really good fit. It's a really good fit. Euler's method, a really good fit. And this again, looks like a branch of hyperbola over here. Right? That's using software, by the way. Let's go back to the notes again. Let's talk about that. The way we did it, we separate the variables. We had the initial condition, and we were able to determine the exact solution to it for those given conditions over here. Again, looking at the graph, let me just show you that. Figure 7, page 11. We got this over here. And again, I'm not sure what step size I was using for this over here, but there is the exact and the approximate. Euler's an approximate technique. All right, thank you.